All right, and for our last talk before the coffee break, we're going to be getting a talk from uh, Jingyi Wang. Again, I apologize if I'm mispronouncing your name.
It's
And
perfect.
the talk will be on reverberation and relativistic reflection in black hole X-ray binaries with NICER.
Okay, thanks for the introduction, Greg. Hi, everyone. My name is Jingyi Wang. I'm a grad student at MIT working with Professor Aaron Kara. Today, I'm very happy to share with you some results on black hole X-ray binaries with the X-ray telescope called NICER using the method of reverberation and relativistic reflection. A very interesting aspect of black hole binary is that we see a pattern of state transition. And a useful tool to describe an outburst is the hardness intensity diagram, HID. In an outburst, the source would travel across the hot state, soft state in a pattern as the red arrows show. And in the radial, a compact, mildly relativistic jet is common in the hot state, and during the state transition, a transient, highly relativistic jet is staying at the so-called jet line with unclear mechanism. There are many remarkable questions, like what is the state transition mechanism? One popular idea is that in the hot state within the outer standard sync disk, there is an inner half flow which serves as the corona, and the inner half flow collapses during the state transition, along with a less truncated sync disk. But this model is challenged by some analysis suggesting the disk is not truncated in the luminous hot state. And also, this is related to another big question of the corona nature. For example, the corona can sit at the launching point of a jet, so on the vertical axis of the accretion disk, instead of being this inner half flow. The method called reflection spectroscopy is where we study the time average flux energy spectrum as a sum of a disk black body, a powder-like corona emission, and the reflection spectrum, which includes most prominently the broad Airline. By fitting for the spectrum, we can measure the spin, the inclination, and other physical parameters. Reverberation, as Thomas said, is the time lag caused by the difference in light travel time between the primary corona emission that travels directly to us and the reprocessed emission that travels an extra distance. We should take a look at a previous result in MaxCJ 1820 using reverberation with NICER data from Kara 2019. The figure on the left and also the arrows show you how the source travels in its 2018 outburst in the HID. Reverberation has been done in the rainbow-colored epochs. In the lag frequency spectra in the middle, you can see low-frequency hot lags and high-frequency soft lags, whose frequency range is represented by the horizontal lines. Those soft lags are due to reverberation in the innermost disk corona region. And the main finding was that in the hot state, the soft reverberation lag happens at higher and higher frequencies, and the lag also becomes shorter, which implies a smaller region that causes reverberation. This could either result from a change in the inner edge of the disk or a change in the corona geometry. However, from the fact that the red wing of the broad Airline stayed the same, the inner edge of the disk should also stay the same. Therefore, we put forward the idea that the corona contracts in the hot state, which could also explain the drop in the narrow core of the Airline, which is thought to result from the upper part of the corona illuminating the outer disk. As you can see in the HID on the left, the good news is, thanks to NICER's day-to-day coverage of J1820, it caught the super bright hot to soft state transition, during which people have observed a transient radial jet at the jet line. In the past, people have only performed reverberation in the hot state because that is when the corona emission dominates and we have enough variability to measure the lags. But with this precious data set reaching 10 to the 4 counts per sec, I decided to extend our reverberation analysis to the state transition for the first time. We could firstly look at the Airline evolution because that line profile could phenomenologically tell us something about the disk corona geometry. So this is the data to model ratio when you fit the flux energy spectra to a disk BB plus power law model, in which disk BB is a multicolor black body emission from the accretion disk, and the power law is the corona emission, so that the axis here is the broad arrow line. We see a narrow core dropping down in the hot state when we compare the yellow to the red epoch, which has been already seen in Cara 2019. Then during the transition, very surprisingly, we found the arrow line gradually gets blue shifted as we compare the purple to the yellow epoch. That extra blue shifted component from preliminary analysis could be modeled by returning radiation or emission from the plunging region. We are still working on that. But what is very clear is that during the transition, the red wing of the line does not increase, as would be expected in the popular state transition model, where the inner edge of the disk should move inwards. These are the lag frequency spectra. In all epochs, we detect high frequency soft lags due to reverberation, and that frequency range is shown by the horizontal lines at the bottom. With the chosen epochs, first we confirm that during the hot states, reverberation happens at higher and higher frequencies with a smaller amplitude, as shown from the red to the yellow epoch. And then for the first time, when the transition starts, I found that in the purple lag spectrum, the soft lag frequency surprisingly decreases, and we have longer lags compared to the yellow epoch at the end of hot state. So it looks like a turnover behavior compared to the hot state. The longer lag implies a larger disk corona region that causes reverberation, and that could very likely imply an expanding corona. I also want to emphasize that this finding is also shown in Barbara's paper this year. With all the great quality lag spectra, it would be amazing if we could physically fit them. We have this recent reverberation model called Railtrans that allows us to do that. Railtrans is a GRA tracing code to calculate the light travel delays and energy shifts of photons. It uses a phenomenological treatment of the low frequency hot lag with a pivoting power law, which means the corona emission has both a variant normalization and a slope. It can fit for time lag or even the whole cross spectrum, accounting correctly for instrumental response. Next, I want to show you explicitly how we can make use of the reverberation model Railtrans. The upper panel is the power spectrum of epoch 1 at the end of hot state. We have detected QPOs in this epoch, and the frequency plus or minus the half width of half maximum of the QPO and its harmonics are shown with the shaded ranges. The lower panel is the lag frequency spectrum. Because no QPO mechanism is included yet in our reverberation model, and lags at the QPO frequencies are likely to have additional complexities compared to the broadband noise, we decided to adopt a more conservative approach and only extract and fit for the lag energy spectra in the frequency bands outside of the QPO frequencies. So you can see the right column here represents the quality of fit we can get. And the good news is we can get a pretty good agreement between the data and the model. I want to highlight one fitting result, which is amazingly consistent with the result from the qualitative look at the reverberation lag evolution. Here we plot the corona height with the epoch color codings, same as in the HID on the top right corner. The AMI radial flux density is shown in red, both as a function of time. We see that in the hot to soft state transition, the X-ray corona height increases from about 30 gravitational radii to hundreds, while in the radial, they launched a ballistic transient jet at the radial flare about 5 days lagging behind the initial X-ray change at the beginning of state transition. In the right-hand side cartoon, if we plot what we found during the hot states in Cara 2019, and also what I found here during state transition, we can have a somewhat complete story. So in the hot state, the corona contracts, while in the radial, the steady compact jet becomes weaker and weaker. And during state transition, the X-ray corona expands 5 days before the transient radial jet is launched. The expanding corona scenario is also suggested in Barbara's paper. Therefore, a combination of these two pieces of results in the hot state and in the state transition suggests a very close relation between the X-ray corona and the radial jet, and might suggest the corona nature as being the base of a jet. This also indicates that the hot to soft transition might not be marked by the change in the inner edge of the disk, as in the collapsed inner hot flow model, but instead marked by the corona expanding vertically and launching a jet knot that propagates along the jet stream at relativistic velocities, and that jet knot becomes radial bright several days later. I also want to mention that the archetypical black hole binary GX339-4, the first source failed utterly, and Barbara DiMarco detected soft reverberation lags in black hole binaries, but only in the hot state. The source has entered a new outburst in the end of February this year. So I triggered my NICER Geo program to follow this outburst. And we found extra evidence that the reverberation lag gets longer in state transition. In the HID, you can see the hot state epoch in blue and one of the epochs in the state transition in red. The middle column shows the lag frequency spectra, and the shaded ranges are where we detect soft reverberation lags, where you can find it occurs at lower frequencies with a much longer amplitude. The red column shows the lag energy spectra in those shaded frequency ranges, where you can see strong soft reverberation lag signatures, and the lag amplitude increases from about 1 millisecond to about 5. This is, again, the first time we tracked reverberation into the state transition for this source, and its evolution is exactly what we observed in MaxCJ 1820. I'll leave my summary here and happy to take any questions. Thanks.
All right. Let's thank Jingyi for the first time. All right, I'll begin with questions from the room.
We have one question, yes.
All right, thank you.
Hi, this is Andrzej Ciaski. I wonder, how do you know that the inner radius does not decrease, that stays constant? I understand that the corona expands, you have time lags, but that piece is unclear to me.
Yeah, I think it comes from, firstly, when you just look at the broad Airline profile, because the line gets blue shifted. If the inner edge of the disk moves inwards, you would expect the red wing to increase, right?
Well, the blue shift could be due to the outflow. No?
Yeah, so I guess there are some caveats when you only look at the Airline profile, but we also did the Railtrans modeling of the flux energy spectrum. And we found no decrease in the Rn. So.
All right, Jerome.
Yes, hi. I'm super happy to see people starting to think that the corona expands and is probably the beginning of the exjection somehow. This is something we've tried to do with my PhD back in the year 2000 something 5 or 6. Of course, we're just looking with spectroscopy and very basic diagnostics. And I'm happy to see that the timing seems much stronger to prove this or to go along in this direction. My question is simple. I was wondering if you looked at the parameter of the spectral parameter of the corona during this phase that you showed, and whether you see some changes or typical changes that would go along with your conclusions.
You mean except for the corona height we just showed?
Yeah, I mean the spectral parameters of the corona. Have you tried to I don't know, fit with Comptonization models or stuff like that and see?
No. Yeah, so I think the only very relevant parameter here is the corona height. and because it's only a lamppost. And we did compare the corona heights from the time lag fit and the flux energy spectral fit, and there shows a discrepancy. So it might suggest that the lamppost is just not a good assumption, and the corona could be extended in the state transition.
Okay. Okay. Thanks.
I think we have a question in the room.
We do. Hi, NJ, Ilek. I have a question concerning your statement that the corona contracts during the hard state. Later on this afternoon, we have a session where we are going to discuss the relative contribution of where is the action taking place? Is it in the corona or in the jet? If it takes place in both, could this contraction of the corona be interpreted as a change in the relative importance in terms of emission of the corona with respect to the jet?
Yeah, I guess we could think about that more carefully. Yeah, I think there could be a chance. But also it depends on what corona you're talking about. Is it the base of the jet or the inner half flow or?
Okay, thanks.
All right. Well, let's thank Jingyi and all this afternoon's first half sessions talk again.
Yeah, just a comment.